Hello, I'd like to thank the organizers for the opportunity to show our work in simulations that accelerate intraparenchymal brain infusions using ultrasound-enhanced convection delivery. This work is out of myself, Wally Block from the University of Wisconsin, and Raghu Raghavan from Therataxis. Here are our conflicts of interest, our interests in MR image-guided interventional procedures, as well as predicting, tracking, and validating drug delivery. This work aimed to move mitigative therapies in rare neurodegenerative diseases towards cures. This family, the Van Houten family, unfortunately lost two of their three children to Batten disease. Otherwise normal at 2, a missing gene creates accumulation of an unwanted metabolite in the brain, which then creates a slow demise to long death approximately 10 years later. They were instrumental in influencing BioMarin, a rare drug company, to develop a biweekly intraventricular enzyme replacement strategy that slowed the disease. This momentum has created encouragement for Critical Path Institute to create a dedicated lysosomal storage disease, of which Batten is one in that class. Gene therapies for these diseases will need to treat large volumes of the brain. It's unlikely that ultrasound blood-brain barrier disruption techniques would work because they would require too large of a viral titer to treat the whole brain while the rest of the body was absorbing the treatment. So here in 2020, there was a trial with a small number of children, which created some success in removing that metabolite. In surgical techniques, we're largely blind, placing 6 catheters in these regions and then infusing and hoping for the best. Their conclusion was that improvements in drug delivery were necessary. Convection-enhanced delivery, its Achilles heel is that the infusion prefers to follow hydraulic contiguity pathways with lower resistance. So CSF, white matter, and so it's thought on the pharmaceutical street is that it's constrained to follow the first white matter path that the infusion finds. So our work is in improving predictive capabilities and then real-time control of gene therapy. In this classical control diagram, the predictive control is in acoustic streaming. That's what we're going to be talking about today. That's going to build upon what we've already done in catheter control and catheter placement in our understanding of the physiology of interstitial flow with the use of periodic MRI monitoring to guide the procedure. So Dr. Raghavan has been working for nearly 20 years on these ideas of how to keep the infusion in the interstitial pathways, avoiding sulci sinks, avoiding perivascular spaces. And the way he does this is by doing preoperative MRI imaging that then characterizes the tissue as white matter, gray matter, vascular, CSF, and uses diffusion tensor imaging as a mapping of the hydraulic connectivity. Excuse me. This work is picked up by BrainLab in 2014 in a product that allowed some brain cancer therapies to predict where catheters should be placed. Unfortunately, it's no longer supported in that the catheters, it assumes are rather simplistic and no longer used by neurosurgeons. So this work is about coming for second generation type planning and real-time guidance. We've had some success in simplifying access here, delivering in this preclinical models, stem cells that are integrated here in a Parkinson's model. And you see the well match here between the simulation and measured infusions in brain cancer type treatments. And we also know that the MR contrast agents are good indicators of where viral vectors are going. So this work looks to supplement the catheter with an external ultrasound transducer array. It could be a custom array, it could be in Cytec. And the idea is to use the imaging to steer the focus of the ultrasound to push along with the infusion front. So Dr. Raghavan in this 2011 work, created a series of coupled equations that then predicts in a forward model how a distribution will move forward. Convection is the wanted term. Diffusion is rather small, not very helpful, and then we track the loss to unwanted sinks. The work that needs to be advanced for ultrasound is to add terms to these second and third equations to account for the acoustic energy. And so in this 2018 work, these terms are added to account for intensity vectors of acoustic fields that then will then show how they affect the velocity in space, and then how the change of these intensity fields also influences these changes in velocity. So in this one-dimensional simulation, we see how CED, how quickly its speed falls away from the pressurized catheter. But if we can add a streaming effect and have it coincide with the front of the infusion front, we can double the velocity here of the infusion front at some distance from the catheter. Here we limit ourselves to the mechanical index to avoid cavitation. In later simulations, we worked at lower power limits that are worked at limiting heating, but the ultrasound protocol should be quite easy to modify the focal width, modify the peak intensity, and then steer that with the infusion front. So for this intensity front, we can see this change in velocities. Here's the catheter tip, here's the focal region, and you see a kind of coordinated motion moving away from this focal point, pushing the infusion front with it. Now, pharmaceutical companies are likely also be first interested in intrathecal or interventricular deliveries because their access to the brain is simpler. Here, Dr. Raghavan creates an intensity field to push fluids from the lateral ventricle into the subarachnoid space, creating large velocities at the interface of the CSF with gray matter, an area that we don't do very well with right now. So going forward then, we have mapped the change in interstitial velocities that are achievable with a rather straightforward acoustical fronts. The next thing would be to come up with some type of challenge and see what percentage of the cerebellum we could hit for diseases that primarily affect this region, a smaller region of the brain, with X catheters in Y hours. And then, of course, moving forward with this, showing feasibility in ex vivo models, and then completing this with a link with drug companies, showing them what's possible to achieve. That then would hopefully stimulate these type of programs in monogenic gene therapy going forward. Thank you for your attention.